Welcome, everyone. My name is Brittany Todd, and I'm a member of the Fabric Leadership Team. Thank you all for joining us today for the 12th installment of our Stitching Together Innovation with Fabric Users, led by Ellie Ghafouri. Next slide, please. Before we begin, I would like to share a few housekeeping items. The webinar will include a live question and answer session following the presentation. Please note that the chat feature has been disabled. If at any point you have a question, please type it into the Q&A box at the bottom of your screen and we'll answer it during the Q&A session. Last, this webinar is being recorded and will be shared with all registrants. Next slide, please. We are joined today by our presenter, Ellie Ghafouri. Ellie is an assistant professor in the College of Engineering and Computing at the University of South Carolina. His research lies at the intersection of network programmability, performance, and security with a focus on P4 programmable data planes, data processing units, smart NICs, and accelerated packet processing architectures. As a member of the CI lab at USC, Dr. Ghafouri develops virtual laboratories and training materials that enhance education and research in high-speed networking, TCP congestion control, programmable switches, software-defined networking, and cybersecurity. He earned his PhD in informatics from USC in 2013. Next slide, please. I will now pass to Ellie Ghafouri to start the presentation.
Thank you, Brittany. Thanks everyone for joining. So today we're going to be talking about the Bluefield DPUs. And the agenda for this talk, first we're going to start with the need for hardware acceleration, then a little bit of a background on what DPUs are, what are the common available DPUs in the market, and then we're going to go a little bit deeper into the Bluefield 3 model, which is provided by NVIDIA. We're going to talk about different ways to program the Bluefield DPU, and we're going to show a demo or simply some training material that we developed that you can go over. This way you can learn more about DPUs. And finally, we're going to conclude with some Q&A. So why are we interested in DPUs now? And this is something that has been a very active area of research in the past few years. And the reason is the performance of CPUs, general purpose CPUs, have slowed down over the years. So if you look at the graph here, on the x-axis, we have the year, and the y-axis, we have the performance improvement of the processor. And you can see that, back in the 80s till early 2000s, we were getting 52% improvement per year on the CPU performance. But since 2004, we start seeing a little bit of a slowdown, and now with the end of Moore's law, there is scaling, and with the limit of Amdahl's law, which is related to how much parallelism we can get out of the performance, we are seeing that the performance of the CPU has plateauing, and we are no longer able to push further the limits. At the same time, we are seeing that the port speeds, the link speeds of network connections have been increasing much, much faster, and they are rising exponentially. So this graph here shows the relative improvement of port speed and CPU performance. And we can see that in 2020 and the past few years, this gap has increased significantly. This means that because we have more data to process now, and the performance of the CPU is not able to keep up, so we need to try to find a different way to accelerate data processing. And this gap has led to what we are calling domain-specific accelerators, or DSAs for short. So those are processors that are implemented in ASIC or FPGA, and they do a specific function, but they do it very, very fast. So they're not general purpose. They just specialize in specific functions. And by doing that, we were able to maximize the performance. So that brings us to data processing units, or DPUs. And sometimes you would see the term smart NICs or next generation smart NICs. But DPUs are basically like a small server. They have DSAs, domain-specific accelerator, to offload the processing from the general purpose CPU on the host. So what are the DSAs that are typically available in those DPUs? You will see a programmable packet processing pipeline. Typically, this is a P4 programmable pipeline. You see it here. Regular expression, if you want to accelerate regular expression matching, encryption, decryption, compression, and there are others such as DMA, RDMA, and so on. So all of those are implemented again in typically in ASIC. Some of them are implemented in FPGAs. And another thing that the DPUs include is general purpose CPU cores. And these are typically used for managing the system, but they can also be used to perform some processing that's not possible to do on the DSAs. These CPU cores is basically where you can run your operating system. You can have a Linux operating system here, and it's gonna be a complete machine separate from the host. So you will SSH into it, and you do the configuration, and you run the application that you want. So here you can see that there are some components that are similar to what you have in other NICs. So you have the ports, the receive port, the transmit port. You have traffic manager, and there's a bus, high-speed bus that interconnects those compute engines. There's on-chip memory, and then there's a PCI bus to get to the host. So we've been seeing a lot of applications that are being offloaded to the DPUs. These are some categories. So mostly we can categorize them as security, network-related applications, storage, and compute. Now for security, you can do a lot of offloading for rules for packet processing. For example, if you want to do like ACLs or stateful firewalls, you can do so. For intrusion detection, if you want to bypass some flows from being inspected, or if you want to do DPI because of the regular expression engine available, or if you want to implement your custom function, you can do so. A lot of the encryption for like TLS, IPsec, these stacks, they are being accelerated, as well as the other asymmetric cryptography operations. For networking, tunneling, switching, telemetry, load balancing, also 5G user plane functions, there are some work on that. For storage, you can accelerate the initiator, the NVMe offload over fabric initiator offload, and the target. For compression, you have different algorithms that are available, and you have some for compute. For example, if you are doing machine learning, you want to accelerate the MPI primitives, you can do so, key value stores, and so on. And this is not all the applications. There are others, and lately we are seeing more and more papers being published on these DPUs. So there are different DPUs available today in the market. From NVIDIA, we have the Bluefield family, so that's what we're going to be focusing on in this presentation. But there are other vendors. So from AMD, you have the Pensando, and they have FPGA-based DPUs, like the Alveo one. Intel has what they call an IPU, infrastructure processing unit. It has the same components as the DPU that we talked about. It's just a different term that they use. And one from Intel is P4 programmable. You have FPGA-based variants from Intel as well, from Octane, and there are others as well. Now, each one of those, or most of those, are being used a lot with hyperscalers so that they can offload some of the infrastructure workloads to those DPUs. But again, we're going to focus just on the NVIDIA Bluefield one, because this is the one that we deployed in Fabric, and this is the one that has a lot of the interesting applications that we can simply just start and play with. So we deployed Bluefield 3 DPUs on Fabric. Now, recently, NVIDIA announced that there's the Bluefield 4 that's going to be available next year. But this really, it's similar to the Bluefield 3, but a little bit more processing cores and resources on it. These are some of the sites that already have DPUs installed. This is not the latest version. There are some additional sites that are now including Bluefield 3. but those are tested, and you can, if you have the permission on your project on Fabric, you can go ahead and try to start playing with those DPUs. So the architecture of Bluefield 3 is the following. You can see at the top here, we have ARM-based CPU cores. So this is typically where you have your operating system. You have Linux. By default, you will get a Linux Ubuntu on those DPUs. And then you have Docker here, which is, we're going to talk more about it, but it's the software stack. So it contains all the tools to actually start developing applications for the DPUs. We have the accelerated pipeline, programmable pipeline, and we have access to all the accelerators there. So you can see crypto, RDMA, ASAP Square, timing. There are others, PKA, AES, so these are for crypto as well, decompression, and so on. And also we have here DPAs, Data Path Accelerator. So these are RISC-V based cores that are also programmable, and they are highly threaded, so you can offload some of the threaded workloads of your application to the DPU. So Docker is the SDK. It contains compiler, services, tools, and libraries that you can just install and start using for those DPUs. You can see at the top, you have applications. So these are the high-level applications. And with Docker, it already comes with some applications pre-developed. So all you have to do if you want to test them, you can just compile and run them. You don't have to modify much with the code. But also you have the libraries. So if you're interested in doing your own custom application and leveraging the accelerators that you have on the DPU, you can write the code and invoke those libraries. Another interesting thing that they provide with Docker is the services. And the services here are basically just, they are packaged in Docker containers. So you can just pull one of them and then you run it. For example, the P4 programming is packaged as a service, right? But there are others. There's one, for example, for host-based security and DMA and others as well available. And at the lower level, you have the driver so that you can talk with the hardware. So the three main components that are programmable on the DPU are the ARM cores, the data path accelerator, and the programmable pipeline. So the ARM cores, again, these are general purpose cores, and the Bluefield 3 comes with 16 of them. And this is where you have your operating system. Typically, you would run control path applications here. So it's like the control plane kind of. And you can see also when we go to the left-hand side, this is easier to program. So on the ARM cores, you can write your program with any language that you want. But typically, we use Docker because we will have access to all these libraries. And Docker basically is based on C. So you write C applications, you import Docker libraries, and then you can start invoke those accelerators. You can also, if you're interested, you can use those ARM cores to process packets, and you can run DPDK-based applications. And you have 16 CPU cores. So what you can do, you can like enable multi-threaded DPDK so that all these CPU cores are going to be used to actually process the packets. And because it supports DPDK, another way you can program them is by using P4 DPDK. So you write P4 and you get the performance of DPDK. But typically, these are more for the control path application or like the control plane. However, there's a lot of work that use them as well for processing packets. The second component is the DPA. So these are 16 hyper-threaded cores, and they have a real-time operating system. These are optimized for IO-intensive application, high insertion rate, network flow processing, device emulation, collective and DMA operations. So basically, these cores, also you program them in C, but they are RISC-V based, so you don't have all the things that you would do in a regular C application. But if you can write your application there, you will get the performance. And it's because the DPA is situated very closely to the NIC data path. So it has low latency access to the packets that you receive. So if you want to do some transformations on the packet, you can write your program on the DPA, and then every time you receive a packet from the NIC, you want to do some changes to it, you're going to have some functions implemented on DPA, and they're going to be invoked and changing the packet or extracting some information from the packet and so on. And the third component is the pipeline. So basically, this is typically programmed in P4, but you can also use Docker Flow or even OVS with hardware offload. So here is basically where you have like the match action pipeline. So you can create tables, you have match rules, and then you have the actions associated with those. And essentially, when you get here, so if you are trying to program this accelerated pipeline, you'll get the best performance, right? But you don't have the full flexibility, so you cannot like implement very complex algorithms there. It's very similar to how you would write a P4 program on a, let's say, a Tofino switch, right? You'll have to abide with what's there on the hardware, but you'll get the best performance among the three. Now, typically, you can actually use all of them together, right? So you can use the ARM to handle maybe the control plane or the slow path, DPA for the handling some of the operations, maybe not all of them. And then the pipeline here is going to be used to like filter the traffic and send them to the other compute engine. So you can use the three of them. It's not like they're not mutually exclusive. So if you want to use Docker, Docker again is the software SDK or a bunch of toolkits available so that you can program the DPU, and exposes APIs for the accelerators. So in order to use any accelerator on your DPU, you have to follow a certain workflow. And the first one, or the first part of the workflow is to do device discovery, then create memory map, allocate buffers, create the progress engine, configure which accelerator you want to use, submit a task, and then wait for completion. And then after you're done, you will clean up. I'm going to go into each one of those, not in too many details, but just to understand better the workflow, because this is a general workflow. Whether you want to use compression or DMA or crypto, you'll have to use the same sequence of function calls. So the first one is, again, device discovery. You might have multiple DPUs and multiple different types of DPUs. The first thing you want to do is you want to open a device. And the way to do it, you have different ways. You can open it by its PCI address. So if you go to LSPCI, you get the address from there. You can use it, and you can call this function and provide the string to it. And then it's going to open it so that you can use it. The other way to do it is by opening based on the capability of the device. So for instance, if you're interested in doing decompression with the deflate algorithm, right? And what you can do, you can iterate over all the devices, and then you can check which ones support that functionality. For that one that supports that functionality, it's going to return success, and then you will go to this if statement and open the device. There are other ways to open them, but these are the most common ones. Then you'll have to start allocating memory. And what we will do is we will create a Docker M map, which serves as the memory pool for data buffers. So you can see here we have the Docker M map. It's associated with devices, so the device that we opened in the previous step. And it points to a memory range where you actually have your data. At the same time, in order to refer to those data that you have in the memory, you're going to use Docker buff. So these are the data buffer descriptor. You don't have the data right in the Docker buffer, but these are just pointers to where the data reside into the memory. And you can have multiple inventories. Within the inventory, you can have multiple Docker buffs. Now, every time you want to do any task that is provided by Docker on some memory region or on some buffers, you have to use Docker buff. So you can allocate the memory. You can use like malloc or calloc, but then you'll have to actually use a Docker buff to point it to it so that you can use it in the libraries provided by Docker. The next component is to create a progress engine, which is the device that is responsible for scheduling the workloads. And this is basically the engine that is going to be handling the submitted tasks. So if you say, okay, I want to start the encryption or start the compression, this is the engine that's going to be handling those and doing the scheduling. And it works asynchronously. So you can submit multiple tasks at the same time, and then the engine is going to be basically advancing them and then telling you later on whenever one is done so that you can get a callback. You create the accelerator instance. Again, you have different accelerators available. And based on the DPU, if you're using, for example, Bluefield 2, if you have the older DPU, that's fine. It's still the same workflow. But you might not have, for example, all the accelerators there. And you'll have to create an instance of which accelerator you're interested in, let's say compression. So you call the docker compress create. And then you submit the task and you wait for the completion. Okay, so there's going to be a loop. The Docker PE, the progress engine, is going to be doing the progress. And then whenever you get the job done or the compression ended, you're going to get a callback and then you can continue doing something else. And finally, after you're done, you have to make sure that you release everything so that you avoid leaks and dangling mappings. Again, there are some functions that you can call to actually do that for you. There's an example available on the artifact manager for compression, exactly what we were talking about. And I will shift to the Jupyter notebook just to show you here. So this is the notebook that we have, and it's detailed so you can see how long it is. I'm not gonna have the time to go over all of it today, but I just want to show you the important parts so that whenever you run it, you're not gonna be lost into all the details there. Again, this is available on the Artifact Manager. The first part of the lab contains the description, so basically some information about the theory behind how to use those libraries and exactly what I was talking about in the slides, right? So how the buffers are created and so on. Then these are the basic stuff that you would do with any slice. But the thing to note here is that when you create or when you add a component to your node, you want to make sure to use the Connect X7 100. So the 100 basically are the 100 gig GPUs, DPUs, sorry. And then there are some sites that have 400 gig DPUs, but these are limited. Most of the time, the 100 is more than enough, unless you have a very specific experiment that you want to run it at much higher rates. So we create the slice. So here is basically all of the stuff that you would need to have to make sure that Docker is installed, the dependencies are there, Meson, Ninja, this way you can compile the applications. And once you install those, you have to enable and start RShim. So RShim is this interface that allows you to access the DPU from the host. So once you have RShim installed and started, you'll be able to do SSH to the DPU from the host, and you'll be able to do all the configuration. Now, before you do that, you need to push an image. Now, this is not always needed. For example, if this is a DPU that you have in your own server, you don't need to always keep pushing an image, right? But here on Fabric, let's say I use this DPU and my slice ended and someone else is using that same node and same DPU there. They want to make sure to reinstall the image. And the reason is they wouldn't have access anyway, because whenever you start with the DPU, is going to ask you to set a password. And so they won't have access to the password that the previous experimenter set. One thing to do is simply just call this, and that's going to be replacing the image on the DPU. It's going to take a little bit of time, so you have to be a little bit patient here. But once it ends, you can reboot the machine, you assign here the IP address on the host, right? And when you started this RStream, you will see that there's a new interface called tm5_net0. This is basically a virtual interface that is created that you would use to actually communicate with the DPU. Again, this is all here for the management. We're not talking about the data path. So you'd assign an IP in the 100.0/24 range, and the DPU by default is going to have the 100.2 IP address. So typically we just use 100.1 on the host. We turn the interface up, and now we will be able to SSH to the DPU. One thing that is very useful to know is that sometimes you might have logged into the DPU and maybe you changed by mistake the IP address, and now you no longer are able to actually log into that DPU or SSH to that DPU. The good thing is that you can access through console. So this /dev rstream0 console is basically the device that you can pass to a program like screen, and then you will have console access to the DPU. So that's useful because sometime, I mean, even if you end up like, let's say you are sending an image to the DPU and the DPU, halted for some reason, and now you don't have a working image at all, you can actually reboot the DPU, and you can even go to the BIOS and do changes there. So it's going to give you like just a console access to the DPU. Another useful thing is to just generate those keys so that you can bypass always entering the password. That's for one reason, but the other reason, as we will see later, sometimes like there are some instructions that you have here in the lab that you want to execute on the DPU, and to avoid or to be able to do it directly from Jupyter Hub and not have to do it interactively through the command line, you just generate those keys, and then you're going to be able to push the commands directly through Jupyter Hub to the DPU. Okay, so all this part is just like to get started. Now the lab itself would contain, C code, as we said. This is Docker, and you have all the files here. Okay, we just separated those into separate files just to make it simpler to read. Otherwise, it's going to become too long and it's going to be a little bit hard to read. Now, all the next steps that you see here are basically description of the C code, which can take a while to actually go over all of them. But it's not hard. So what I'm going to do instead of going over these, and by the way, we made them so detailed because we want users to learn about them. But once you understand this specific example, you'll be able to use other accelerators. It's just a matter of changing, for example, from compression to something else. Now, very quickly, if you look at the code here, so you have the main.c. This is just the main function, but it doesn't do much. I mean, it just create the logging backend and stuff like that. So typically, you won't change anything here. The only function that is important is the run lab logic, which you will find in the logic.c. The logic.c, if you scroll all the way down, you have this run lab logic that is gonna call another function run, and is gonna pass to it the program state. Now, what is the program state? You will find that into the definitions.h. You see a program state has a program base, the instance of the compression, context, the PE, and so on. So all the variables or the objects that you might use in your application are there. And you can change that. I mean, it doesn't have to be that way. We just wrote it that way. But if you want to add more stuff based on your application, you can do so. So we're going to call run, which you will find at the top here. That's run. We initialize the program state. This is just zeroing out the data structure, the struct that we were seeing. And then you start with the actual, memory allocation. One thing to note here is that whenever you see the prefix doka, for example, here or in this one or in those, this means that this is a built-in function. And the reason I'm emphasizing that is because if you look at the samples provided by Docker, some of them do not have the Docker prefix there. That means they are just wrapper functions that you have to go figure out which other function they're calling in another file. And then when you go to that file, it's calling other files. So it's just a little bit harder it makes it easier for you because it's wrapping things. But if you want to understand every single function, we wrote this program in a way that we are not using much wrapper functions. It's just purely the ones that you will find on the Docker documentation here. Okay, so you can see first, I'm opening the device here, iterate over the devices, and then check if the decompression deflate is supported. We create the memory map, the buffer inventory, the progress engine, and the compression. Basically, exactly what I was showing in those slides. You need to do all these steps. You configure the compression. For example, one of the things you need to do is to specify what are the callbacks function or the callback functions that you are going to be using whenever the state changed or whenever you have a completion event or if you have an error, right? Now, those functions are implemented in a separate file. So you find them here in the callbacks.h and callbacks.c. So here it's very simple. I mean, we are saying if the state changed, we are just basically displaying a message to the screen. In some cases, we are modifying a flag here. Now, if you have the completion event also display on the screen, you calculate the checksums here. And then if you have an error, you would basically display what is the status or what caused this operation to fail. So after that, here we are just setting basically the functions. We haven't started yet with the compression. Then we will create basically the instance. You'll have a file. Let's say that file was compressed in a tool in Linux that you have, but you want to use the decompression engine to accelerate that. And what we are doing here, we have that file. So here you can see the in file. That's a file that was compressed outside of Docker. And basically we are reading that file, right? And then we are doing we are calling the accelerator. So we are submitting the task. And then you can see here the while. So that's the loop that's gonna be letting the progress engine advance so that we can know when there's a callback. And finally, it's writing back to another file called decompress that you can also find here. It's just a basic contain like, ASCII text, but you can test that with others as well. And finally, at the end, you want to make sure to close or to do the cleanup. So to do these cleanup for the Docker buffers, you have to use this function, which decrements the reference count for a specific Docker buffer. So that's it for the Docker. Again, there's a lot of code here. It might seem a little bit scary, but it's really the same thing. Once you get used to this, if you want to use another instance, you'll have to check, for example, what are the functions related to other accelerators, and then you can invoke them here. Okay, so once you have that code done, here what we are doing in this step, we are just enabling internet on the Bluefield. And this is just configuration of IP tables to do NATing on the host so that we are sharing the internet with the host. Now keep in mind, this doesn't always work, especially if you have IPv6. If you have IPv4, it would work. But basically, why do we need the internet? Because maybe you want to install a package there. For example, if you want to do the compilation on the Bluefield itself, you might want to install Meson and Ninja, because those do not come pre-installed in the image. So you need to use the, apt-get install Meson, and then you'll be able to use it. So now that we have the code here running or written, we will upload it to the host. We can create a tar file from those. Then we're gonna push it from the host to the DPU. Notice here the 102, that's the DPU. Now on the DPU, we can extract. So notice here how whenever we are executing commands on the DPU, we are using SSH followed by the host and then the command itself. In order to be able to do that from the Jupyter notebook, you need to make sure to do the what we were talking about with the keys, right? So you need to create the key and send it. Otherwise, you can just open the terminal and then do those steps manually. So now we have the files there in the DPU. We can run the Meson build. We build or we generate here the build files, and then we compile with Ninja. You're gonna see here that's gonna compile those C files that you have. And finally, we will simply run the application. So when you run the application, you will see here the logging that we have in our program in the logic.c when we created the mmap and the others. And then you will see that here we have those callbacks being invoked. So for example, when we started the compress operation, that changed to running. So we are logging that. Once it's done, we get a callback that it's done. And then, we do the cleanup and then the application finishes. Okay. So that's for the Docker. The other way of programming the DPU, as we said, is with P4. And there's also the DPA, but we're not going to go over the DPA. We don't have much time today. This could be a different session. But I will show you the P4 because a lot of you are interested in using P4, and you probably have used it with Tofino or BMV2 or DPDK. And for those of you who are not familiar with P4, P4 is a domain-specific language to define packet processing. So you'll be able to define and parse new custom headers or existing headers. You can define what are the actions you want to take on packets, right? So you want to do some custom algorithm implemented at the fast pass in the data plane. You can use P4 to do that. And usually you do it to offload some processing of the packets from the general purpose CPUs. The workflow is you write a P4 program. A P4 program could contain different blocks, different tables representing different logic. For example, maybe you can do packet classification, L3 routing, or L2 forwarding, and then you have an access control list. But you can do more interesting stuff than these. These are the basic ones. So you have your code. You use the P4 compiler. That's going to generate a binary that will be pushed to the target. Okay. Now this slide here is generic. So this is regardless of if you're using the DPU or you're using a Tofino switch. And at the same time, the compiler will generate control plane contract or API that you will use to actually manipulate the stateful elements into the target. So for example, if you want to push table entries, or if you want to read what was written to a register, or you want to reset some registers, you can do that from the control plane. So the high-level model in P4, and this is called PISA, the Protocol Independent Switch Architecture. It's just a model, but this is like the general model that architectures would follow. So if you are using a NIC or you're using a switch, they will have their own architecture, but it's using components from this general model called PISA. And you would have a programmable parser. This is where the packets are going to start coming. And this is represented in state machines. So you'll write the parser code. For example, here we are parsing Ethernet. And based on the ether type field of the Ethernet, we can go to the next state, right? Or the next header that we want to parse. For example, if it is 800, we can go to IPv4. And from there, we will have another state here. And we check if you want to go to TCP or UDP, and so on. Now, you will have the headers defined and what are the data that you're going to be using. For example, you can have metadata available, and this metadata will be useful for you as the packet is traversing the pipeline. In the pipeline here, you have match action, so you can do match on specific keys, and then you can take action if you have a match there. And then the packet is going to go through transformation over all the tables that you would have in that pipeline. And then at the end, you will use the deparser to reconstruct the packet and then send it out of the wire. This is a very general overview. There's a lot involved here if you want to go into the details. But again, this is the general model that is used by any device that's P4 programmable, right? So if you want to use like the NICs, for example, they have portable NIC architecture, PNA, that uses elements from this, but it's not exactly like that. So you would have other components. There's PSA, the portable switch architecture, or if you're using Tofino, you have Tofino native architecture, TNA. So all of those architectures are basically using elements from the general model, which is known as PSA. Now, for the Bluefield, as we said, NVIDIA provides the P4 programming as a service. So, and that service is called DPL, Docker Pipeline Language. So what you'll be able to do there, you'll be able to use the, any text editor that you like to actually write P4 code, P416 code. And then you're going to be able to use the DPL compiler. So this is the P4C compiler, the general one, but with the backend that is specific to the Bluefield device. Okay, so you write your code, you compile, you're gonna generate the binary. Then NVIDIA also has some containers for running the P4 runtime server. So basically, all you have to do is just once you have that binary, you can push the binary through P4 runtime, and now it's gonna be running at the hardware, the ASIC of the DPU. Now there, you're gonna get the packets. You will do all the packet processing with the headers that you defined and the tables that you customized. And then finally, you have some debugging tools. These are provided by NVIDIA, for example, NSPEC or debugger. If you want to see like what are the entries in the tables, and if you want to see like what is the packet looking like as it's traversing the pipelines, you can get some information on that. You don't need to use those, but they are nice tools for debugging, especially if you are learning before. Now, that code you will see here on the Bluefield 3, we have the ARM subsystem. So that's where your ARM cores are. But we have this E-switch, the embedded switch. And basically, that P4 code that you write and the DPL compiler is going to generate the parser, the table, and the deparser there. And it's going to be mapped to the ASIC. So this is ASIC based on the E-switch, meaning that you're going to get line rate performance here. But one of the things that is a little bit kind of a disappointment, not a disappointment, but it's still not supported. There's some features in P4 that are interesting for creating like, custom applications like registers. These are not supported yet. But if you want to do just match action table, you can do like, exact matching, LPM. You want to do meters are there, counters, all of these are there that you can use. So the code you can see here and the include, for those of you who are familiar with P4, you can see that there are some includes that we are using that start with Docker, because these are just for the, Bluefield with Docker. But everything else kind of is similar. For example, you create controls, like this is the main control that we have. In this example, we're just doing L2 forwarding. We have action to drop. When you see here NV, this is the NVIDIA. So these are intrinsic or built-in functions provided to you. This is another custom function forward where we are doing swapping here of the IP addresses, IPv4 addresses, and then we are calling the NV send to port. So this is again a built-in function to send the packet out of a port. We are creating a table here. Just to make it simple, we have constant entries here, but you can also add those through P4 runtime at runtime. And finally, you apply the table in the apply block, and you need to instantiate that pipeline. So you have the NV Docker pipeline where you are basically invoking the parser and the control that you just created. Now, one thing to note here is that we have NV fixed parser. So NVIDIA already provides a parser for the well-known protocols, right? The standardized protocols, but it's also possible for you to customize. If you have your own custom header that you want to use, you can write that here as well. So same as before with the Docker, there's an example for using the P4 on the DPU. It's on the artifact manager. Let's see how we're doing with time. Let's see. So this is the notebook. Again, all the stuff that we start are similar to before. You get with installing the dependencies, you install the image on the DPU, you configure the management, all that stuff. Now, what you see here, this install DPL runtime, these are scripts that are here available for you. And all you have to do is just push them there, you execute those, and then it's gonna be installed. It's super easy to get it up and running. One thing you need to configure is this file, a configuration file, where you provide an ID for your device because you might have multiple DPUs. Now, in that file, you have to specify the mapping between the physical ports, right, and the logical port. So for instance, on DPU, on the Bluefield, you would see that there's an interface called P0. So that's the interface facing the network, right? So here we are saying that P0 is gonna be port 0, meaning that later on when we install rules in our tables, you would just use 0, and it's gonna know that it's associated to the physical port P0. Now PF0 HPF, that's the interface that's facing the host from the DPU. We are giving here the port ID 1. But if you have, for example, SRIOV and you have maybe 10 functions, you can create different port numbers there, like 1, 2, 3, 4, all the way to 10. One thing that to note here is that to be able to run that pipeline, you need to use the physical port. You need to use P0, and you need to have at least one port. You can still use the SRIOV and virtual functions, but you need to have P0 there. So one thing could be like you create a P4 program and then you have SRIOV, let's say 32 functions. These are attached to VMs running on your server. And then the P4 pipeline will be doing the packet processing and then redirecting packets to the right VM. That's something you can easily do. So after that, once you copy this YAML file to the kubelet.d, that's gonna start, and you can check with CRI/CTL pods. You will see if it's up and running. And this is the code that we just saw in the slide. We are just explaining them here in more detail. But once you have it, you can call this P4 compiler, which is DPL P4C. And then this is gonna generate a folder _out containing the binary that you're gonna be deploying to the Bluefield. Okay? Once you have that, you can push it through P4 runtime, and then you're gonna have a P4 runtime shell open. So if you wanna manipulate table entries, you can write here the P4 runtime commands to do so. And the remaining here, you will see is basically, we are just testing. So in our program, we had some rules to drop packets based on MAC addresses, and we are just testing to see if they are actually activated or not. One final thing before we conclude, if you are interested into going deeper into those, we have some labs. What we saw today was lab 5, which is, combining all these previous concepts. But if you want to just start simpler and going easily into them, you can do lab 1, 2, 3, 4. These are not yet on Fabric, but we have them on our NetLab platform at USC, and I will show you how you can get access to those. So we have libraries on Docker. For P4, if you want to do more interesting stuff like, packet mirroring or modifying tables with P4 runtime, counters, inspecting statistics on the pipeline, there are labs on those. And there are these two libraries. These are not specifically for Bluefield 3, but you can run them there. If you want to use DPDK on the ARM cores, but you want to write it in P4, there are labs to do so as well. Now, there are some workshops. So we have one next week on supercomputing. There's one at the end of the year in Technology Exchange. These are the links here. So when you the one at the bottom, cyber training, when you click on it, at the top, you will see there a form. You can just fill that form. And then in 24 hours, we will be returning back to you and giving you access to those labs in our NetLab. This way you can run them. And then once you are familiar with them, you can go back to Fabric and then write your experiment. Finally, I would like to acknowledge the NSF for supporting this work and also the Fabric team for helping us with integrating the DPUs and working on the control framework. So with that, I will hand it back to Brittany.
Yes, thank you so much. We will now move to the Q&A session. So let's begin with questions submitted during the presentation. The first question is, what makes Bluefield better than other DPUs?
That's a good question. I would say, and I'm trying not to be too biased here. We tried to work with other DPUs, for example, the IPUs. It wasn't as easy, and the documentation wasn't as available as what you would see in the DPU. And the DPU, yeah, if you see the sample applications that they have and just samples to learn about those APIs, it seems much more documented than other ones. Now you have other, like the one from AMD, Pensando, it's hard to acquire them. I mean, we tried to get them, but unless you are a very big customer and you're gonna be ordering a bunch of them, you're probably gonna have trouble to get them there. And so the DPU was one of the few that was easier to acquire first and had very good documentation. That's what I can say.
Great, thank you so much. The next question is, when will the record be uploaded? Also, will the Jupyter Notebooks URL be posted online?
I'm sorry, say it again, Brittany.
Sure. So the question is, when will the record be uploaded? Also, will the Jupyter Notebooks URL be posted online?
I think that's more of a question for you guys, right? But the Jupyter notebooks are available, right? So you can use the artifact manager right away to actually start using them.
Excellent, thank you. The next question is, are compression and other special functions exposed as P4 externs? Any common compiler toolchain for DPU and IPUs?
It's a good question. There are some accelerators available, but not all of them through P4. So there are some, if you go to the DPL documentation there, you would see that there are some examples that use some acceleration related to like IPsec, because typically this is one of the use case that is heavily used with DPU, especially with hyperscalers. And it's also part of the PNA architecture, the portable NIC architecture. So there's support for that, but not every single accelerator that you have is there, and you can use it as an external.
Great, thank you. Next question, any runtime reprogrammability support in DPUs?
Yeah, so because it's based on the P4 runtime, so you'll be able to actually compile and just repush your P4 code there. That's from the P4 side. Now, for the other engines, if you are writing your doc application, you know, you write it in C, you would need to basically recompile and then deploy. But the reprogrammability that you would know in like other targets like Tofino, right? It's the same here. You can just write the code, the P4 code, and then repush it without restarting or rebooting or anything like that.
Okay, great. This next question is long, so bear with me. In the hyperscaler domain, where DPUs are primarily deployed for specialized SDN implementations handling north-south traffic and infrastructure management, is P4 relevant in practice? It seems unlikely. Based on your experience using Bluefield DPUs in your testbed, what concrete value have you seen for scientific computing applications that justifies the complexity of programming and deploying them? Do you foresee Bluefields being adopted primarily by end users or infrastructure operators in HPC environments, or not at all? They are just toy box tools for learning.
Yeah, thank you for the question. I will try to go one by one by one. So the first part, yes, it's true. It's being used by hyperscalers. Now, P4, there are some already written code, like for example, host-based networking, that you can simply reuse, and it's purely in P4. It's completely written in P4. That's kind of the same thing that you would see in hyperscalers and SDN implementations. Now, if you look at other DPUs, for example, the one from Intel, the IPU from Intel, it's more P4 programmable in the sense that the most focus is on P4. You don't have something like Docker. I mean, they have their own, stack called IPDK, but they are implementing the whole hyperscaler kind of functionalities all in P4. So that's definitely doable. And if there's something that is not supported in P4, you can always use other engines, so you can send the packet. The nice thing about that pipeline is that you can define where's your packet is going to be going out of, and then you can send it to the CPU cores or DPAs or something else to do more processing. The other one is regarding the concrete value for scientific computing. Yeah, there's a lot of work on that. I'm not an expert in HPC, just to be clear, but I've seen a lot of applications doing scientific computing on DPUs, and they typically use those DPA cores to do some, I don't know, like change detection or stuff like that. I can share later, maybe I can send them to the fabric team and they can there are some slides related to physics kind of experiments where they're using the DPU to accelerate processing. Now, if you will be in supercomputing next week, the tutorial that we're giving, there will be also co-presenters from NVIDIA and from Georgia Tech, and they've done some work on scientific applications, and they will showcase some of those. But I'm not an expert in those, so I cannot give much of the details there. But if you are interested, I can post some slides, and if you are there, feel free to join and learn more about it.
Yeah,
And
that'd be great. If you
yeah,
want to send us those slides, we could probably include that also when we send out this recording.
awesome. Thank you. And the final one, I don't think they are just toy box tools for learning, right? They're already being used by hyperscalers, whether it is the Bluefield one or the IPU. Because if you think about it, you know, they're actually saving a lot of money for the hyperscalers because the infrastructure functions, the network, the security, all those stuff that previously were done on CPU cores of the VMs of the tenants now are being offloaded to the DPU, and those CPU cores are now available for more, processing on the tenant side. So they're maximizing from that aspect. And from a power efficiency side, there is a study or a report by NVIDIA showing the gains that you will get in the power saving when you use the DPUs over doing things in general purpose CPUs.
Great, thank you so much. Our next question, can I fully offload the Docker-based application on DPUs instead of running on host?
Yes. So typically it depends on the application. And I can give you an example. It could be something like what we saw with the compression or decompression. You can just run it entirely on the DPU. You don't have to have the host. You can run it on the host such that it invokes the DPU, right? However, there are some other applications, and these are now providing a lot of interesting use cases. For example, you are doing DMA with the host, direct memory access. You would need to share some information between the two, between the host and the DPU. And essentially you'll be able to, or you're gonna need to have two different codes, one that is gonna run on the host, one is gonna run on the DPU. So it depends on the type of application and what you are trying to offload, but it's entirely possible to offload everything to the DPU and start it from the DPU and make the host completely unaware of the application.
Thank you so much. And that was actually our last question for today. So I want to give one more thank you to our presenter, Ellie Kafori. And also, in addition to our presenter, we would like to acknowledge the behind the scenes team listed here who worked diligently to bring this webinar to production. And thank you to the audience for your participation in today's webinar. In addition to a recording of this webinar, we will also email everyone who has registered a list of resources, and we'll include that slide deck once we get it from Ellie This slide deck will be shared along with our Connect with Us form. We hope that you will reach out to the Fabric team for any questions or for support. Our next webinar is Mastering Fabric Tips and Tricks webinar on January 20th at 3 p.m. Eastern. This webinar will be focused towards existing users, AI researchers, and testbed administrators. We would appreciate it if you could forward the information to the relevant users in your communities. And as a final reminder, please submit your Fabric matrix and make sure your project description in the portal is up to date, as we will use that information for outreach, including our website. Thank you again and have a wonderful day, everyone.